to record to the cloud. So welcome everybody. Thank you very much for participating in this event on behalf of the advisory panel and the rest of the research team. This is greatly appreciated. My name is Dan Kuchma. I'm at Tufts University. Tufts University is located in the Boston area. Just before we get underway, I'll remind people sort of mute, please, unless you're speaking. So I think we have a really exceptional group of speakers today, and that the workshop should be very informative and inspiring as well. I know I was inspired by looking through people's slides that they're going to present. We'll begin with a little bit of a short introduction to the project, what we're trying to achieve in the workshop, etc. And then for part one, John, if you want to tab, it's going to be a number of presentations which we could consider to be more motivations and examples of nature inclusive design. And this is primarily going to be looking at the results of some field studies plus some great initiatives. So part two, what we're going to do is discuss 4 specific topics that are particularly pertinent to this particular project for BOEM. So let me continue sort of with a little bit more of an introduction before we get to part one. So next slide, John. So if you go back 10 years or so, it was assumed that the inside of monopiles were airtight and watertight, and therefore once corrosion started and oxygen was depleted, it would stop. Unfortunately, there was leakages, and to completely close those off was not possible, so corrosion continued. And so BOEM has funded studies to look at this. And so the study we're looking at the moment, John, if you would bring up the perfect, is they've asked for recommendations for what should be used for corrosion protection systems on the inside of monopiles with consideration of air and water chemistry, which depending on what you choose can be a little bit problematic. So our research proposal and project has these 4 elements. One is to look at the impact of the selected corrosion protection system. And by that, we mean coating and cathodic protection and the extent of coatings, et cetera, as well as perforations on what type of chemistries you have internally, as well as what type of corrosions you have. As a second element, we are looking at the impact of adding perforations for air and water exchange on structural design and loadings. That will be the subject of the next workshop. Number 3 is looking at the impact of the selected corrosion protection systems and perforations on marine growths and habitats. This is what this one is about. Number 4 is we are developing plans for needed field and laboratory studies for advancing science and practice. And this summer, we're looking forward and hoping to get underway with a field study. So next slide, John, you were good there. In thinking about our talk today, it's important to be aware, of course, as soon as we start putting hardscapes into the environment, they attract a lot of growth, different types of marine growth, depending on area, depending on materials. And this is something that we don't understand in the science as much as we really need to. And one of the functions of the discussions today is to sort of advance everybody's understanding and also identify where we need to understand things a little bit better. And in thinking about this, at least the research team sort of have 2 thoughts. One thought is if we do good things to the marine habitats with the structures we design, then perhaps we can develop hundreds of gigawatts of offshore wind. But if we do things that are harmful to the environment and people's livelihoods, we probably won't get the opportunity to fight climate change via offshore wind to the degree that we really wish that we want to. And I guess the second thought is, based on the examinations, it really seems that we can do this, but there is some advancement in science, and there's going to be some field trials, et cetera, in order to do it in the most responsible and reliable way. So next slide. The research team, the contracted research team, Jeff Swain and Kagler from Florida Institute of Technology, Colleen Hansel and Lena from Woods Hole Oceanographic Institution, and then myself and John and Gudong from Tufts. Next. We have a fantastic advisory panel who come from across the world and bring incredible experience in design and they represent a lot of different stakeholder communities, and we're very appreciate for their efforts, as well as a number of other folks who you're going to hear from today in the presentations and in the moderated discussions. Next. So we've had 8 workshops, 6 on the previous project we did for BOEM on corrosion and fatigue. And then this is our second workshop on this project. A workshop can sort of have a range of different characters. One end on the extreme left, it can be informative presentations, and that's what the workshop today is principally about. Some of the other workshops that we've had has been more of a technical committee meeting where people are sharing the expertise and debating, identifying where there's consensus, where there's differences of opinion, and what degrees of uncertainty are. Okay, next, John. So meeting logistics, please stay muted unless you are speaking. Meetings being recorded. Next. Okay, so we'd like to make really extensive use of chat today. So please use chat to introduce yourself to the degree that you wish. Feel free to include links. And then if, as we're going through the presentations and discussion, you're thinking of projects, people, things in the literature that you think would be helpful to be shared, this would be of great benefit. Similarly, would be your suggestions for future research that is needed. If you have questions for speakers and moderators or anybody else, put forth those questions as well, even if there isn't time for us to answer them and discuss them at this workshop. What we're going to do is we're going to have minutes from this workshop, and we're going to take those questions and try and answer them as best as possible. And as any good PhD student knows, when they first start communicating with their advisors, it's like the most important thing are the questions that you try and answer. So we're greatly appreciative of your contributions to things in this way. We are not, when we put forth the minutes and list the questions and other comments and suggestions, other than of course your self-introduction, we are not going to be recording your names in the chat. So feel free to suggest what you may initially seem like a crazy idea. And when we get into discussions, we'll use the raise hand approach. Some people like to turn on their video as a way of flagging us if they have a question so we don't miss you. And so, John, next slide. So we're going to get right on to part 1. And so we have 4 great talks lined up. And so we'll get right underway, I believe, Rebecca, with yours.
Fantastic. Thank you, Dan, and good morning, everyone, or good afternoon, depending on what part of the world you're in. It's a pleasure to be joining you. My name is Rebecca Green. I'm a senior scientist with the National Renewable Energy Laboratory here in the US, or NREL. My PhD is in biological oceanography. I've been at NREL now for about 3.5 years, and I work on a variety of offshore wind activities, including in the environmental space, fishing access, multi-use of the ocean, and siting, as well as feasibility studies around offshore wind development. So it's my pleasure today to be here with my co-PI, Mark Severy, from the Pacific Northwest National Laboratory. And I'll give him a chance to introduce himself in just a minute. We're here representing our DOE-funded SEER project, which stands for the U.S. Offshore Wind Synthesis of Environmental Effects Research Project. And it's our pleasure to provide an overview for you today of the goals of this project, where we're at, and where we're going in the future.
This meeting is being recorded.
With that, Mark, would you like to introduce yourself as well, please?
Sure, thanks, Rebecca. Hi, everyone, I'm Mark. I work at Pacific Northwest National Laboratory. It's been great to collaborate with Rebecca and her team on this project. I am a mechanical engineer by training, but my work is broadly in the offshore wind space and primarily focused now on offshore wind and wildlife effects. So I work on this project, and then I broadly work on developing and testing wildlife monitoring technologies for offshore locations. So I'm going to pass back to Rebecca, who's going to start us with the overview.
Excellent. Thanks. And I think, Mark, we decided you get the award for being the earliest participant on the call. So thanks for joining on a Monday morning. Next slide, please. Great. So first, we have a brief introduction to our SEER project. We're a little over 2.5 years into the project now. This work is being performed at the direction of the U.S. Department of Energy's Office of Energy Efficiency and Renewable Energy, Wind Energy Technologies Office, otherwise known as DOE WETO, between our two national laboratories, PNNL and NREL. We're jointly performing this work, which is a multi-year collaborative effort to facilitate knowledge transfer from around the world related to the environmental effects of offshore wind energy development. In terms of project objectives, these are multifold. We have been working over the last couple of years to summarize the international understanding of environmental effects, monitoring tools, and mitigation strategies for offshore wind development, again, from around the world, so globally, and how it applies to both the US Atlantic and Pacific coasts and potential offshore wind energy development in those areas. We are specifically examining which of the state-of-the-art methods and technologies that are currently being used are relevant to environmental issues with application to US offshore wind development. We are identifying the knowledge and research gaps based on the diversity of species, habitat users, and stressors that we see here in the US, with consideration for our US environmental, legal, and regulatory structure, as well as technological innovations down the road, both in terms of the types of fixed bottom and floating platforms that could be deployed looking ahead, as well as the types of monitoring and minimization technologies that could be used. And perhaps most importantly, we're working collaboratively to develop outcomes with existing science entities and regional organizations who are also working hard to minimize the environmental effects of offshore wind development. All right, next slide, please. So there are 3 main products from our SEER activity, and there's a QR code here as well if you'd like to go to the link. Otherwise, if we haven't already, we'll put the link to the SEER project in the chat. Our first deliverable or activity was to develop a series of educational research briefs. There's 7 of these briefs, which we'll overview in just a minute. They review the state of the knowledge on stressor and receptor interactions, monitoring methods and technologies, mitigation measures, and cumulative impacts related to 7 topics, whether it's underwater noise, the potential effects of EMF, considerations for birds and bats and the like. Our second deliverable or product was a series of webinars overviewing each brief with an expert panel. Folks from both the US and Europe. We're very thankful to the experts who reviewed these educational research briefs and also served on these panels. These webinars were run from last November through this February, disseminating the findings from the research briefs to the offshore wind industry and others who were interested, and were extremely well attended. So certainly a lot of interest in these topics in the community. And finally, we're working on developing a set of research recommendations for both the US Atlantic and Pacific coasts to summarize information gaps and barriers, current challenges around US offshore wind development to inform and guide future efforts. Next slide, please. So these are the 7 topics that we addressed in a series of educational research briefs. We spent almost a year on stakeholder engagement to identify these topics. These are topics where stakeholders felt that there was enough information to put together a research brief that could be short and succinct as a science summary on what we currently know and some of the research questions moving forward. So these 7 topics, most of these have been published. Our last 2 will be coming out soon. We analyzed underwater noise effects on marine life, or synthesized existing information on underwater noise effects on marine life, bat and bird interactions with offshore wind industry. The next topic here relates to entanglement. So the risk to marine life from marine debris and floating cable systems, whether through primary or secondary entanglement, or even possibly tertiary entanglement. One of the briefs we'll be talking about in detail today is the one on benthic disturbance from foundations, anchors, and cables. We'll also be talking about the introduction of new structures or artificial reef effects on fish ecology. We also had a brief on vessel collisions and one on electromagnetic field effects from offshore wind. Next slide, please.
And Rebecca, just if you can, 2 minutes or so. So I know
Oh,
it's going to
okay.
be brief. Time goes by very quickly. Thank you.
Yes, well, I will turn this over then to Mark in just a second. So in terms of the introduction of new offshore wind farm structures on fish ecology, these are some main takeaways that we provide within that brief around the placement of new structures and potential artificial reef effects, what's been documented at European wind farms, for example, in terms of the attraction of fish, and in first wind farms in US waters. What we know for both fixed bottom and potentially for floating wind farms. A variety of monitoring tools exist, and methods and types of data collection. And then we also synthesized best management practices, such as for siting and choice of structures in this brief. And I will turn it over to Mark next to talk about the other brief.
And you can go to the next slide as well. This brief talks about the benthic disturbances from offshore wind structures. Actually, you can go one back, it's okay. For the benthic disturbances from foundations, anchors, cables associated with offshore wind farms, and their effect on the benthic environment. This primarily occurs during, after construction, and also a little bit in the decommissioning effect, depending how the benthic environment kind of moves into that area. So 3 things I'll just say briefly. You can check out the brief, and maybe many of you know this. The primary effects on the benthic habitat are generally localized, the area closest to the offshore wind infrastructures. This is generally right around the turbines themselves. The primary effects can include loss of habitat from the new subsea equipment that's installed, conversion of that habitat through the introduction of new hard substrate, and then lastly, seabed disturbance and recovery after the construction activities. So let's move on to the next slide, and I'll just talk about our upcoming and ongoing efforts. And really, our ongoing efforts are focused around developing research recommendations, both on the Atlantic coast and on the Pacific coast, and then maintaining a list of those research recommendations. These will be published on TETHIS. They're kind of ongoing now, so we're hosting workshops that are going to generate those research recommendations, and then we hope to keep them updated in an ongoing manner through our website. So with that, thank you all for your attendance. You can go to the next slide, which has our contact information. If you would like to follow up, feel free to send an email to either me or Rebecca. And thanks, Dan.
Thank you, Rebecca. Thank you, Mark. And if you think of questions for Rebecca and Mark, please do include them in the chat. So Drew, I see you're online, so it's over to you.
All right, thanks. I'm going to move very fast. The slides are here for your reference. You're going to see the same pictures over and over again, and I'm stunned at how many slides we have. This is a synthesis of work done in the US, as well as referencing work in Europe. So I'm going to move pretty quickly here, just acknowledging the other folks. If you can go on to the next slide. So this is just a summary of work that has been done at the Block Island Wind Farm including rodeo, and that'll be on the next slide. So it's really important to understand there are only 5 turbines. These are lattice jacket, so they do not relate to the dominant topic of this workshop, which is large circumference monopiles and what may or may not go on inside them. So keep that in mind. So lots of different work. I've posted some links to these publications, and I'll put my email if for some reason they don't work. Next slide, please. So this is an overview from Rodeo. That was a BOEM funded project, which actually looked specifically at growth on the structure and the changes to the benthos. We did work more on fish ecology surrounding these turbines. And that report is available and linked down below there. Next. So a quick spin through this. This has been said many times in many different places, but essentially the marine growth, and I just want to make the point, we're going to be talking about marine growth, biofouling, a lot of different terms. From an ecological perspective, I'm not a fan of any negative values associated with growth. From an engineering perspective, that's a different point. So we're going to focus on growth here. Structure goes in the water. It goes from the intertidal all the way down to the seafloor, regardless of whether it's floating or not, there is some connection. So what happens is we do change the bottom. There's a lot of energy flow as a result of the introduction of this. Our focus is largely on the flow of energy and through enrichment, through the growth on the structure. And so the structure itself has this growth, but the seafloor around it also becomes modified, and all of this becomes a shift in the food web in the location. Next. And we really focus on how this biomass may be exported to the larger ecosystem, because unless we understand this, we really don't understand the function of all that biodiversity on the structure. So it's really important to follow energy in a food web or in an ecosystem. And this is where the nature design comes in that I think some folks are going to talk about. Next slide. Another important thing is this concept of connectivity. We don't really have corridors in the marine environment. We have larval distribution and movement. And so this can affect both desirable species, focal species, but also potentially non-native species. Next slide. So the food web is the focus here. How does this change the habitat? And that's what we're beginning to look into. Next slide. So we are going to do a project at the Virginia. There's only 2 turbines there. We have an opportunity to look at how some aspects of nature enhanced design may or may not affect this broader range. So there's 2 turbines. We'll enhance one, not the other, and use a lot of the techniques that you're going to hear about from other speakers. So Dan, I can stop right there.
Drew, if you don't mind, I'm going to thank you for the expediency of a presentation, but you caught a lot of very important key points and the slides were very, very illustrative. And so since I know time is going to be an issue today, what I'm going to recommend, if people have questions for Drew about past work, future work, please do send him, please add something to chat. And then we'll make sure that we get responses to those questions or share those thoughts as part of the minutes. And so with that, then we'll move on to the next presentation. And so Anthony, it's going to be Anthony followed by Marcel. So they have a joint presentation.
Thanks, Dan. And hi, everyone. Anthony Dvorskas here. I'm just to introduce myself, I'm the biodiversity lead for North America offshore for Ørsted. And I wanted to start off here just, if people have not heard about it, just let everyone know about the biodiversity ambition that we have at Ørsted, which is that by 2030, there will be net positive biodiversity project in all renewable energy projects that are commissioned. And as a result of that, we're very interested in exploring we don't know what the best way is to get those biodiversity uplifts. And so we're very interested in exploring the different kinds of strategies that we may use either at the offshore wind facilities themselves or within proximity to those facilities. And so I just wanted to go through a couple examples of some things we've started to do to look at that biodiversity uplift question. Next slide, please. And the most recent thing that I hope and think maybe you all have seen in the news is the ReCoral project, which is what's best phrased as a coral restoration experiment at this point. And it's off the coast, the west coast of Taiwan, south of where the Changhua 1 and 2A offshore wind farms are located. And what this project is doing is taking surplus indigenous coral spawn that are collected off of the islands that are also west of the Taiwan mainland. Those spawn are then incubated back in a laboratory into the coral larval stage. And then those larvae are transferred, and there's a lot more details in terms of that transfer that we don't have time to get into today, but basically they're brought, the idea is that they'll be brought out to those turbine foundations and transferred there, and settlement will be facilitated. And then ideally, they will start to grow on those foundations. And Ørsted is looking at this as a proof of concept kind of trial, again, as an experiment. And hopefully, if this approach works in terms of a strategy for growing these coral, there's a possibility of scaling this up to other locations as appropriate. And there's a lot more information about this available online and on our website, and there's some videos that you can check out. The next slide, please. One of the other efforts that we've made is around the area of artificial reef creation, and you're going to see a lot of this is not in North America, but is over in Europe. At one project site, there were some boulders that needed to be moved as a result of the project activities. And the idea was that instead of moving those boulders, and removing them to onshore locations, that perhaps they could be rearranged and into a configuration that would facilitate, some kind of use by organisms. So there were 5,000 boulders that were relocated near the Enholt offshore wind farm in Denmark in 2012, and there were 23 artificial reefs that were able to be created by rearrangement of those boulders. So this is one example of the ways we're trying to look throughout the project life cycle to think where we might be able to incorporate these kind of benefits to biodiversity. Next slide, please. Also, more recently than that, in 2021, we have these biohuts that you can see a picture of that were created in work that we're doing with WWF and there are 10 of these that are installed in Grenaa Harbor in the Strait, the Danish Kattegat. The idea here is that this will provide a shelter for the juvenile fish and ideally restore cod populations, and also in doing that help to restore the ecosystem balance. And you can see these cages have some oyster shell within them, and they're lowered into the water, and then they will be monitored over time to see what actually happens as a result of their placement in the environment. And next slide, please. And lastly here, and then I'll pass it off to Marcel, we have the cod pipe reefs at the Borssele wind farm in the Netherlands, Netherlands waters. And again, this is our artificial reef creation project. And there are 4 of these purpose-built cod pipe reefs, as they're referred to there, that are about 10 meters in diameter and have variable height. And again, the focus here is on providing habitat for Atlantic cod, since there's an interest in Atlantic cod within the region. And there is ongoing monitoring that is occurring of the cod and lobster behavior. And I'm going to pass it on to Marcel now, in the interest of time, to give you some more details on the work that is going on specific to that. Thanks very much.
Thanks, Anthony, for your nice introduction. Doing a lot of work indeed. I would like to go into more detail on the cod work and the lobster work we're doing. And this is a collaboration between us, Ørsted, Teki Wind on Sea, which is a financing program, and the Rich North Sea, who had a grant from the Postcode Loterij. Next slide, please. Yeah, we're performing this experiment in Borselen 2, which is one of the offshore wind farms of Ørsted. As you see, it's in the south of Holland on the border with Belgium. And L08 is a monopile where we have where Ørsted has positioned 4 reefs. Next slide, please. So here in the middle of the green part, you see LO0, and around it 4 circles. Would there be some? Is there some pointer? No. Well, if you go, yeah, that's reef 1. If you go to the right, that's reef 2. And then if you go down the southern reefs, reef 4 and reef 3 and reef 4, they have arched. They are differently arched. That means that they have anti-scour, and the reefs in the north, they don't have anti-scour. Around those reefs, the red circles, we have placed 16 frames with antennas. And next slide, please. We have tagged about, next slide, please. We have tagged about last year 45 cods around all these reefs, divided more or less equally in time or in space. And we would like to know what is the distribution of the cod in time and space. For instance, are they homebound? Do they stick to the reefs? And are there differences in behavior between the reefs, between themselves, and also with the monopile? Because if you remember the setup, the antennas also cover the monopile. Next slide, please. This is an example of how we have been tagging. Sophie is sketching once an animal is caught and it's 32 centimeters or bigger. We open the belly, and in the belly we place a tag. We sew it back. We sew the belly back with so it's not open again, and we place an additional tag in the just near the spine, so we know from the outside the animal has a tag inside. These acoustic tags, they send out a ping, and this ping is every minute, and it's caught by, and once it's caught by at least 3 of the 16 antennas, you know where it is. After recovery, the animal is placed back. Nice for you to know that currently at this very moment, people are catching cod again at Ørsted Borselen. Next slide, please. Lobster tagging. Next slide. For the lobster, I'm very interested in I'm very interested in the habitat use in relation to the reefs, and also so what is the habitat use is also the substrate used, for instance, for walking or for migration, or is it used for hunting? Is there, and what is, for instance, the speed in relation to the type of substrates? What are the rhythms? What is the daily rhythm? What is the seasonal rhythm? And also, what are the distances covered? Because one of the research we're doing is serving 2 lords. So one of the lord is the biodiversity, but on the other end, we also serve the fisheries, and there is a development going on that we will want to have multi-use in offshore wind farms, and one of the forms of usage can be fisheries. And then we have the safety factor that all these cages have to be placed at least 250 meters from the monopiles and from the infield cables. And up to my knowledge, what we've seen so far is that lobsters will go to a cage at the maximum of 125 meters. So I would like to know what is the normal behavior of these lobsters, and is there a chance they will be caught by lobsters by cages placed at more than 250 meters distance. Next slide, please. So we had to buy the lobsters. We had not the means yet to catch lobsters, and also the expectation that there would not be a lot of lobsters, since the reef is quite new. And here you see a picture of the lobster. If you see the black tube type of thing, that is the tag. It's like how a size more or less part of a lobster of your finger. Then we have a tag, a numbered additional tag, the yellow string, which is attached to the, which is also more to the right. If you go more to the right, that's attached to the acoustic tag. And then we have also placed one in the back. So once the lobster that's on the left side, the previous one you touched, so once they've shed their skin, their harness, then this back tag will remain. We've bought lobsters of 1.5 kilo or more. So the maximum of they shed they molt every 1.5 to 2 years. So on average, we expect half a year of information of each lobster. Next slide, please.
And 2 minutes.
Okay, I'll speed up. So this is the typical results that I'm expecting. On the left side, you see the behavior pattern of a lobster on in this case in England, on soft and hard substrate. On the right side, you see a graph that on the x-axis you see an increase in the percentage of hard substrate, and on the y-axis you see the speed, and you see that on soft substrate they walk faster than hard substrate. Next slide, please. Somebody collaborating with us is the Rijke Noordzee, and they are really interested in collecting eDNA. And then by eDNA you have a water sample which can tell you something on the local biodiversity. The spatial resolution is quite good. The moment you take a sample on when the water doesn't run again, I forgot the English word, then you will see that that the eDNA, environmental DNA, is really representing the reef below. Next slide, please. My first results. Next slide. So we've tried to take out the antennas to get the data. 13 were recovered completely. One, we recovered the data, but we lost the frame, and 2 antennas are still stuck in below in the mud. Then if you go down to the right side, there we see presence data. So we see the first row, the first 45 rows are the cod, and then if you go down, you see the first presence of the lobsters. So the rows in which the A is more to the left, those are the lobster data. So a lot of lobsters have molted or are lost due to currents. That place is really a current rich area, so these animals can be washed away. Coming Wednesday, I'm going out again and release another batch of lobsters. So this was it. If you have any questions later on or by the chat, I'm available. And this is my email address and telephone number where you can reach me. Thank you.
Thank you ever so much. A lot of inspiring work, and it's just great to see the level of evaluations occurring. And as we know in the US, this is all critically important to us. So Jamie.
Hi, Dan. Hey, everybody. I'm Jamie Lashinsky. I'm the Managing Director of MOCEAN USA for Renewables Offshore, for our offshore engineering and energy group. We are constructing wind farms all over the world. And I've had the pleasure of also being our project manager a number of years ago for the 3D printed reef monocle pilot project. And so what I'm going to show today are a few things that we've been doing and basically how we deal with this within MOCEAN, which is like a little sort of microcosm version of how you need to deal with it in the big picture. All right, so next slide. So value of artificial reefs, basically the way we see it and the way we work with it on our various projects, which our pilot projects are basically can be independent of development. And we also have projects, for example, as Marcel just showed and as Drew showed, that are part of bigger developments. So both are valuable. And basically with artificial reefs, we see that they play an interesting role with habitat creation. They're scalable, and that you need to basically work with your site-specific ecology and met ocean conditions, and that they basically can support fisheries development. They could serve as coastal protection and also enhance biodiversity. They can create interconnectivity. So again, as Drew mentioned, really looking at that connectivity element, which you can look at wind farms as a way of basically connecting different habitats or creating a broader habitat within a wind farm through pathways of connectivity. Restoration elements. You can also consider restoration where you know that there's already been historical degradation, or you might even cause degradation. So how do you deal with restoration or offsetting? And then also creating opportunities for research and community involvement. The world of reefs are far from perfectly understood, so there's a lot for us to learn. Next slide. So offshore wind farms, we see them actually as presenting unique opportunities, but in order to be able to seize those opportunities, you have to connect. You basically can't take it from one perspective. Both Drew and again, Marcel touched upon elements where looking at it from an ecological perspective or from an engineering perspective, they actually could be contrary, conflicting to each other. Again, from a governance perspective, but basically in order to be able to have a successful project moving forward, you need to look at what you want to develop, why you want to develop it, and you need to look at it from these different perspectives in an iterative fashion, where you basically are combining and having common goals, and basically you're avoiding negative subsequent impacts through governance, engineering, and ecology. And again, everybody brings their own knowledge into it, so you can't do it alone. You need to basically have these community efforts where you need to be lean and efficient, especially within developments themselves, wind farm developments. Also, basically how Anthony was describing, basically trying to utilize the wind farm that's going to be developed anyway, but then bringing this extra opportunity in for research and better understanding, ecological research and better understanding by basically working together with clients, fisheries, governments, contractors, knowledge institutes, and NGOs. Next slide. So for ourselves, what we've learned, we've been basically working with artificial reefs for around a decade as Boskalis, through projects, through our basically the infrastructure, marine infrastructure that we're developing, or alongside or even independent from our projects. But basically reef development and marine projects, it's an integral part. You need to have sustainable design where you're combining all aspects. So in order to have a win-win, you need to have basically, as compensation and rehabilitation, you need to look at ecosystem values, but also work within the governance system. So you actually have to work with permit systems or utilize these projects as mechanisms to actually enable permitting processes. And there's also value in these individual standalone reef system developments, especially from a research perspective and development of sanctuaries. This is also quite important when looking at decision-making associated with how and where you develop your structures. Both Anthony and Marcel showed two different approaches. Also Drew, where basically you can look at developments that are directly attached to or are focused on the marine infrastructure itself that's going in the water. But you can also look at it as being independent from those structures or trying to utilize those structures where you have the reef itself being developed nearby. And this is quite important from the perspective of decommissioning. If you know you have to take that structure out of the water in 25 years or 50 years from now, you need to be really aware of, do you want to actually develop your reef structure on the structure you need to remove later by permit, or develop it next to it? Or do you have the right to leave it in the water if you develop a reef system there? So these are all big picture, long-term ways of thinking, but are really important in order to be able to define the success of the project. So you need to think on the total lifetime of the project. For our approach, basically we work again within our projects as well as via pilots. The network is hugely important. We would never be successful in any of our reef pilots doing it alone, or even just working only with our clients. We always have to leverage knowledge and resources from the community to make it successful. Also really focusing on this positive impact. The positive impact, again, can't be just from one perspective. It has to be multi-perspective. Next slide, please. So here are some of the different concepts that we've tested globally so far. So we've worked with really tailor-made 3D printed structures. So these are very large scale. These are 2 meters wide, 1.5 meters tall. And these are basically tailored to the system at hand. They're unique, but they are expensive. You have to transport them carefully. And they're not necessarily transferable directly in design or concept to other locations. There are modular systems, so we're working with reef systems by Moses, endless reef systems, and reefy blocks. And these are all systems where you basically, through the modular approach, you build it up through the unique system and then develop it in that way. And they have they basically have other advantages and disadvantages. So again, there's not one design, one material that is perfect for any reef system. You need to basically take it into consideration, be aware, and that there are huge developments going on all the time with materials. And so to leverage the state of the art, leverage the knowledge that's out there to basically build the best artificial reef system for your specific system. And next slide. So for our program, basically overall, our goal is the development application of large-scale artificial reefs as enablers for marine infrastructure or coastal protection works. That's the nature of our business, so that's the connection to our business. Our strategy is that artificial reefs directly address our focus areas of biodiversity and climate change mitigation, and that we're looking to provide state-of-the-art fit-for-purpose solutions, but with a clear business case. We are a business, marine infrastructure contracting business, so we need to basically make a connection to our business for all of the activities that we're involved in. And then our approach, again, I've already said it, so strong strategic partnerships, build upon symbiotic dynamics to make sure you have win-wins for all parties and you're not negatively impacting another aspect because of really focusing on one particular one area. And that basically really leverage the different types of systems that are out there to serve our clients and our markets. And then last slide. This is just an example of some of the parties that we've worked with really closely to make, to basically develop some of the artificial reef pilots and projects that we've worked on to date. This isn't even comprehensive, but it takes a village to do it successfully. Thanks.
Jamie, thank you ever so much. And thank you to all the speakers in this first part. I found, I think it's inspiring, it's impressive, so much leadership being shown. Thank you, Rebecca and Mark, for summarizing the synthesis work, which is also critical since the US is a little bit earlier in this, which is fantastic. Thanks to the DOE and national labs, obviously, for that. To Bohm and the Rodeo Project that Drew summarized some of the great work happening on the first wind farm in the US, Block Island, and now continuing in Virginia as well. That's exciting. Anthony and Marcel for a lot of boots on the ground, actually getting in and tagging fish and following the lobsters and everything else. And so that's obviously very important for critical industries. And Jamie, thank you for expressing what is needed from a collaboration approach in order to actually being able to deliver something that is a success for all the most pertinent groups. So part two of the meeting today, we're going to look at some topics that are much more specific to what is we have to deliver on for this BOEM project. And so we have 15 minutes for each of these 4 groups of speakers. And so Monica, let's go start off right off with you.
Thanks, Dan. So I'm working as a contractor with Department of Energy's wind office, but today I'm going to talk about a field study I did a few years ago while at Florida Tech. This project is written up in Materials Performance Magazine, Corrosion Control and Ecosystems Enhancement with Offshore Monopiles. And we also received the honor of a Materials Performance Innovation of the Year award. So I'll dive in, next slide. So as we already heard in the project background, there was an original thought of not having active corrosion protection in monopile interiors, but it found that there was oxygen ingress. And then there was a trial in the North Sea that Alex Delwich wrote about, that they retrofitted aluminum anodes in an existing monopile, and that case experienced hydrogen sulfide formation and water acidification, and that chemistry presents a risk for unique corrosion concerns. Next slide. So for my small field trial, the hypotheses were that a perforated structure could create an environment with more favorable corrosion mitigation, air quality, and water chemistry compared to a sealed one, and that a perforated structure will create a habitat for marine life. Next slide. So in my experiment, I deployed 1 meter long steel pipes, which represented scaled down monopiles. And I put steel coupons inside for convenient analysis. I had 4 treatments, including 2 sealed pipes and 2 perforated ones. So within each pair, I had a freely corroding pipe and a cathodically protected pipe with a zinc sacrificial anode. So the sealed unprotected treatment represents originally installed wind farms. Sealed protected is similar to the North Sea case study previously described. And a perforated cathodically protected treatment over on the right is considered in my trial as a potential improved design. Next. So here's how the pipes looked. They're deployed from August 3rd to October 1st, 2018 at Port Canaveral. So they're hung on a floating dock with a bit of a air gap at the top, and some local mud was put at the bottom to kind of represent a driven pile. And the wires you see there are for corrosion measurements. So next. So the measurements during deployment were dissolved oxygen, pH, cathodic protection, and corrosion rates. And at the end of the deployment, the weight loss of the steel was observed, and the habitat development was observed. So next. So looking at the dissolved oxygen measurements, the black line shows oxygen levels of seawater at the port fluctuate a bit on a daily cycle to do with biological activity. The blue and purple lines show how dissolved oxygen quickly reduced in the sealed pipes, which was in line with that theory of oxygen getting consumed during initial corrosion. And the red and yellow lines are the perforated pipes. You can see they match that of the ambient seawater in the first month. And the bit of a decrease in the second month might be explained by the growing biological community inside the pipes consuming oxygen. And next, looking at pH. So the black line shows the ambient seawater stays near neutral pH of 8. The blue line shows the sealed unprotected treatment, which the pH actually increased a bit after the oxygen was reduced. And the purple line shows acidification occurred in the sealed pipe with zinc. So that was similar to the North Sea trial with the aluminum anodes. And aluminum in aqueous solution can form complex ions that cause acidification, reducing pH down to 4. And similarly, zinc in an aqueous solution may push the electrolyte pH down to 6.8. And that theoretically calculated equilibrium pH was consistent with the pH values measured in this experiment with 6.8. And the red and yellow lines to show that the perforated pipes maintained a pH similar to ambient seawater near neutral, so as expected. And then the next slide shows what we saw inside the pipes at the end of the experiment. So in the sealed pipes, there's black and orange corrosion products on the freely corroding treatment, and the cathodically protected treatment had heavy chalking. And in the perforated pipes, there's biofouling and corrosion products on the freely corroding treatment. And there was biofouling adhered to a healthy steel on the perforated cathodically protected treatment. So next, starting to focus on the habitat. During my weekly visits, I had some indication that there was organisms starting to hang out inside the pipes. You can see a crab here crawling into one of the perforations, and there was a fish poking out of another one. And then next we'll look at the end of deployment, what was inside the pipes. So at the time of removing the pipes from the water, in the perforated, unprotected pipe, there were mobile animals, including a snapper and a few crabs. And again, the steel was covered in kind of diverse biofouling as well as voluminous rust. And I just one click, and looking at the bottom cap of this pipe where it had the originally placed mud, and then as well as a layer of decaying biofouling on top and some fresh biofouling top that had kind of recently sloughed off the sides of the pipe there. You can see one of the sea squirts has some kind of bright orange rust on it. So this kind of implied unsustained growth, as well as a big risk of steel loss as the biofouling falls off and reveals a new layer of steel. So next looks at the protected pipe. So in there, there were more mobile organisms, kind of a higher population count, and the steel surfaces were covered in diverse biofouling, adhered to like a healthy steel. And in the bottom cap, it had the originally placed mud, and there were also a few extra kind of animals hiding in there. With one more click, you can see, add those to the collection. So a lot of life in that one. And then next, kind of compares the habitats of the two perforated pipes. So there was kind of a greater population and more biodiversity of the mobile organisms in the cathodically protected pipe, and abundant biofouling on both of the perforated pipes. And so next is the conclusions of this small study. Show that a perforated monopile interior walls can more easily and predictably be protected from corrosion with cathodic protection, and that cathodically protected perforated monopiles can enhance the ecology of a region by providing a sheltered space within which the marine organisms tend to be attracted to and prosper, and that nature inclusive engineering offers opportunity to complement the local environment and provide ecosystem services. Thanks.
Monica, thank you very much for sharing that great pioneering work that I know you and Jeff did essentially with no budget. So that's particular. So I'm just staying on that one. John is great. And we do have like time, maybe 6 minutes for a little bit of Q&A if someone has questions for Monica. And if you do have a question, maybe raise your hand, and then I think I will see it. Turn your video camera on. That's often helpful. Everybody's been including their questions in chat. We will, at the end of the session, I'm thinking probably have close to 15 minutes for a little bit more of an open discussion based on what everybody's heard to date. So if you prefer to save your question until we are farther along, that's good as well. But I'll wait another 30 seconds or so to see if anybody has a question.
And I can keep an eye on the chat, I guess.
Monica, I think everybody knows there's quite a bit to get into. And so what we'll do is we'll move along then to Andrew. And if we end up having our collective discussion at the end, that's probably a good way to do things as well. But thank you once again for sharing the great work. Andrew.
Hello. Hi, everyone. My name's Andrew. I'm from Heriot-Watt University, where I do research in biofouling. And Dan's asked me today to provide a kind of an overview of biofouling in relationship to this sector. So if I can have the next slide, please. I'm based up in Orkney, which is an archipelago off the north coast of Scotland. And I work for Heriot-Watt University, but I work also very closely with the European Marine Energy Centre, where they are testing and developing wave and tidal devices. And in the waters very close to us are also, of course, commercial scale deployment of offshore fixed and floating wind turbines. So on the next slide, quick introduction to biofouling. It's the settlement and growth of organisms as soon as you put something in the water. Biofouling occurs almost instantaneously, as from a chemical standpoint. The very second you place something in the water, there start to become chemical reactions. Very quickly, bacteria settle to this, a slime forms, and that facilitates the growth of the settlement, and then the growth of larger organisms. Superficially, it's divided into microfouling and macrofouling. These are often there are specialists in these different areas. Microfouling is a very, very important topic. It's essential in the overall fouling understanding. However, what I'll be talking about in my own specialization is in macrofouling. So we'll be talking more about that topic. If I can have the next slide. Thank you. So what is the problem with biofouling? What is it doing? Well, as many of you, of course, are interested in this topic today, of course, it accelerates corrosion, and that, of course, then leads to, a lack of survivability of components, etc. But the other impacts of biofouling include its increasing roughness on the structure, which increases drag. So you then get increasing drag forces, which may be relevant, for example, on mooring systems, etc. Increased weight as well on the mooring systems and dynamic subsea cables, especially. The strategies for dealing with fouling and removing fouling are expensive, and they cause a lot of downtime, so that has economic consequences as well. They can foul access areas, so making safety issues with for example, boarding onto a structure, for example. There can be specific fouling onto anodes and on coatings, so this can then also accelerate corrosion with that. And I did want to talk about the fact there are some ecological issues which have been touched upon by our earlier speakers. And so we'll talk about those a little bit later on. Now, you may be thinking, but well, surely we already understand biofouling. We have the oil and gas sector, and sure, there are these surrogate industries where we can learn a lot of information from them and have learned a lot of information from them. But there are some limitations associated with these. So if I can have the next slide, please. Is this a new problem, the biofouling? Well, there are some unique issues with offshore renewable energy. So specifically, we're using new components and new materials which may not have been previously been tested in the marine environment and gone through its paces. Devices are being placed in habitats that maybe have not been studied as well. Areas of very, very high energy, for example. We're using, and also parts of the world where we may not have done previous studies. We're also using very narrow, in some cases, very narrow diameter structures. I'm especially thinking about floating wind here with dynamic subsea cables and mooring systems. Also, we use a lot of increased use of sensors now for detecting resource assessment and performance. So there are some unique problems with biofouling. If I can have the next slide. So what are the main factors which affect fouling from one place to another? Well, let me just quickly go through these. I don't have time to go in much detail, but depth is a big issue, and that's often largely related to the amount of photic energy coming down. So plants, algae can live at the top, but not deep water. Other issues with oxygenation, etc. Temperature is a big factor in type of fouling community. The type of substrate as well. Hydrological processes as well as hydrodynamic processes will affect the type of fouling that you get. Other parts of water chemistry are important. Distance from land is important, and also distance from ports are important. That's especially important when it comes to vessel transfer of organisms. From a biological standpoint, there are factors such as competition, successional processes, and seasonality, which can cause differences and changes within the type of fouling organisms that we get. So as an overall if you sum these all up together, what you also get, of course, is that there are huge geographic differences. So if I can have the next slide, the Earth, humans love to create and pigeonhole stuff. So the Earth has been divided into these various different ecoregions from a marine standpoint in these fairly near shore areas. And on the next slide, these have been subsequently sorted into other ones, and some of these areas have been very well studied. So for example, number 25, the North Sea, is very well studied. Maybe 43, the Gulf of Mexico, is a very well studied area as well. The eastern seaboard of the US, maybe a little bit less so, and certainly some parts of the world are probably relatively poorly studied. So if we can have the next slide, please. So some of the major macrofouling groups that you find in the North Sea, I don't have time to go through these, and many of you, of course, will be very familiar with these types of organisms, but here's a bit of a, a gallery of some of the main types of organisms. And if I can have the next slide, we have a listing of organisms similarly that are found in the Northwest Atlantic, so on the eastern seaboard of the US. And again, they're often quite similar organisms, maybe different species, but quite similar. And in fact, if I can have the next slide, this just continues on with this list of them. So we have a pretty good idea for certain regions what type of organisms you're gonna get, and we have some idea about what the kind of impacts these organisms will be as well. But I want to talk a little bit more detail about some of these environmental factors that I previously mentioned. So for the next slide, yeah, so latitudinal gradient is an important one as well. So what this is showing here, this is quite an early diagram from studies at Woods Hole, is that you get obviously latitudinal gradients of where organisms will survive and where they'll live. So as you travel from a north-south axis, you'll start to experience then a shifting baseline of the major biofouling organisms in those regions. So it's not rocket science, of course, but it's just illustrating that fact. The next one is depth gradient. So this study here is showing some oil and gas jackets that have been studied in the North Sea. And kind of the take-home point, without getting into huge detail, is just that in different depths, you have different prioritization, that's the right word, different characters. There is a different characterization of species which become more dominant, so at different depths. And I guess the take-home point of this is that you can characterize this. You can recognize patterns associated with depth, but you can also be aware that through locations you'll get differences in the relative ratio of these different organisms. So next slide, please. This is another way of showing depth gradient as well. This is from Forteith, 1982, and again, it's looking at both the inside and outside of these jackets. And the abundance of it. So again, changes in these in fouling associated with depth as we go through. So I can have the next slide. A lot of the work that I do is looking at extreme exposure environments. So hydrodynamics are also very, very important in types of biofouling communities. So what this MDS plot is showing here is that in this case, there are three main clusters of biofouling communities that are associated with sheltered harbor and marina type environments versus high wave environments versus high tidal flow environments. So these are critical environmental factors that determine the type of organisms that you get fouling onto a structure. So if I have the next slide, please. Just to briefly talk about seasonality. So it probably is no surprise that there are certain seasons, I should say there are certain specific organisms have certain seasons that they typically will grow at. And will grow. Their larval spawning seasons are different. So this is showing this has been tracked from locations here at Woods Hole and Chesapeake Bay. So you can have some kind of idea of what species you'd expect at a certain time. And if I can have the next slide. So some work done here in EMEC, this time I've visualized it as this kind of traffic light system, is that with this kind of information, you might be able to manage timings of scheduled maintenance to maximize the efficiency of your fouling mitigations, for example. But now the next slide. So the other process I wanted to mention is succession. So just like kind of the forest, which goes through various stages until it reaches the climax, you get the same situation with putting a brand new hard substrate into the sea. There is a process of successional changes which go on. So, and I should point out too that what season you put it in will affect that succession. So in this particular case, on the diagram on the right, we see that very early on succession, you have hydroids in deeper water. In the shallow water, you have algae. And then as it progresses over time, there is a replacement of one dominant organism by another until you reach kind of a stasis, which can vary. The stability of it varies depending upon other environmental conditions. If I get the next slide, please. So just to go back and to end with looking at the impacts and some of the ecology as well. From a practical standpoint, when you try to understand biofouling, maybe its impacts, the key take home I think I have here is that if you look at this DNV standard, which is for wind turbines, it gives quite a crude estimate of this figure of 1,300 kilograms per cubic meter of fouling. But from all the research that they've taken for this standard, this table at the bottom here indicates very, very, very crudely, just simply two depths, up to 40 meters and then down below 40 meters. And then a second one of locations, which is central North Sea and Norwegian Sea. So there's no references to substrates or references to different species or anything like this. So my point being that as of right now, there are many, many gaps, knowledge gaps in this, and the standardization of the industry is quite blunt at this point, partially because there is a lot of variation sometimes between locations. So I can go to the next slide, please. I wanted just to end by talking about the ecological impacts by providing substrate habitat. So this has been touched on by some of our other speakers today. So firstly, by placing structures in the sea, you can enhance biodiversity. You're creating more complex substrates, a greater variety of substrates. Or I should say, in addition to that, these may serve as, I think as Drew had mentioned, as stepping stones, which can then facilitate the movement of organisms from one place to another place. Now, these can be perceived possibly as good, quotations, or bad quotations. It might be an organism that you want to settle there, like a rare hard coral, for example. But it could also be, yeah, it could be something that's not as favored. It could be an invasive non-native species, which you are promoting its spread because you are giving it substrates by which to move upon. In addition to that, service vessels may work as a conduit for further spread of these organisms. So on the next slide, I think it's my last slide or last or two, just so I've been looking at this work in Orkney research. We found there are several non-native species that are found in the harbors and marinas in our waters. I guess I'm happy to report to say that at the full-scale test centers for tidal and wave environments, so very high exposure conditions, there have been no non-native species recorded. So it may be that there are hydrographic barriers that are created by in more exposed conditions, where we might be finding a lot of offshore wind deployments as well. So that's maybe something to keep our fingers crossed about. And I think I have just one last slide. And that is to say, yeah, so there are many, many knowledge gaps which exist in biofouling in the offshore renewable energy sector. So in particular, we don't understand the environments that well. They're less studied, I should say. And there are parts of the world, certainly, where they're very, very, very understudied, where we don't understand the fouling anywhere near as well as some areas. There are materials, niche areas that are unique to these industries that are not as well understood as for example, more established oil and gas. And then again, the overall risk assessment of the role of these structures in connectivity, and then allowing INNS to facilitate INNS invasive non-native species transmission is of a concern. So there are organizations like Glow Fouling, which are trying to understand this and trying to, just get a better understanding of the risks associated with this industry. So that's it for my sort of whirlwind exploration of biofouling. There's an email address down there too, so if you have any questions, I'll look at them in the chat, but please do contact me as well.
Andrew, thank you ever so much for that incredibly informative, and you got through that material at an amazing pace, but also with great clarity. So thank you very much for that. Does anybody have a question that they'd like to ask Andrew right now? If not, what we'll do is we'll sort of then save the time at the end, so then we can have questions to any of the people that have presented thus far. But if someone does have a question on some recently presented material, we can take that now. Andrew, I think everybody's going to wait until the end. Please do ask your questions by chat, etc., and we will do our best in the minutes to provide responses to those questions. So please do that. And so next, we're over to Nick and Stefan.
Thank you, Dan. Dan, are you allowing one question?
Yes, Peter, go ahead.
I'm interested in the question on whether you have quantitative data concerning the marine growth thickness over the year.
Andrew, I think
Does
that question is
anybody
likely
have
yep.
information about that?
Sorry. So the question was on marine growth thickness. How it develops over time?
Over time.
Yeah, absolutely. Yeah. So yeah, I do have some of those data from the area that I've studied. They do exist for other projects as well. That DNV standard that I showed towards the end of the talk, that was showing estimates of thickness again for those. And for the point I was making on that slide was that it does show estimates of thicknesses for depth and also for two regions within kind of the North Sea and Norwegian Sea. But again, they're very, very broad. So yeah, they do exist to some degree. And there are a lot of additional factors in it. It does depend on what species they are. So is it an encrusting species, or is it a sort of a more compliant organism? As far as if you're talking about the effects, for example, on flow. So yeah, it can be quite complex. But yes, those data do exist, but they are quite varied between locations.
Okay, thank you.
Peter, what we'll do is, I think through the questions, etc., and Andrew will maybe with yourself and with some others, if people can actually identify references, if someone wants to look at some of this material in greater detail, we can work on sharing that. So thank you very much. And so over to you, Nick.
Yeah, thanks, Dan. And also thanks, Andrew, because I think it's a very relevant topic. It also comes back to in one of my slides, the effect of marine growth actually on hydrodynamics. But today, Stefan and I will talk you through basically Deltaris's approach to corrosion protection and water and air replenishment in offshore wind monopiles. I'll do part of the slides, then Stefan's taking over, and then I will wrap it up. Can you go to the next slide, please? So I think this is already briefly touched upon, but what we can do in terms of mitigation of corrosion inside of these offshore structures is apply coatings and either apply sacrificial anodes, zinc or aluminium, or an ICCP system. And I'll talk about the pros and cons, or the alternatives in the next slide. If you can please go to the next then. Before actually going to what these systems do to the environment is a question I posed linking to the first part of this this session is, can we make these designs more nature inclusive? So taking into account the nature and what nature needs to thrive. We've already seen quite a couple of very beautiful pictures of either fish or lobster or mussels. I think even seals are popping up close to wind farms. And the questions that we ask ourselves is, to improve nature inclusive design, can we have a limitation of large scale impacts, such as, for instance, the noise, but you can also think of the shedding of zinc or aluminium metals into the environment, and what does this do for the marine environment? I think we've also heard talks about restoration of historical species, but also preventing invasive species to come to these places, and by that also increasing biodiversity or enhancing it. And I think for that it's really important to both measure and model different types of environmental conditions, like the temperature, maybe the salinity is important, We've heard oxygen levels are very important for marine life. And well, there are various models that we can use to model all these parameters, but of course they also need to be quantified with measurements of the field. Next slide, please. And then I would like to give it over to Stefan, who's going to tell you a bit more on the effects of sacrificial anodes in ICCP.
Yes, thank you, Nick. Yes, I will briefly touch upon the internal chemistry of monopiles, because, well, it was already described before, especially by Monica very nicely in the presentation, that the inside of the monopiles can have a very distinct chemical nature, and especially the effect of cathodic protection is very important. The effect of sacrificial anodes can be zinc or aluminum emissions. These can, of course, be toxic. The question is to what extent that really is the case in practice. I think that is really an interesting research question. On the other hand, if you have ICCP systems instead of sacrificial anodes, then different types of phenomena occur. First of all, the pH close to the anodes can drop, whereas the pH along the steel surface rises. And this can create related effects. And also when the potential of the system is not well fine-tuned, gas formation can occur, especially chlorine and bromine, which can in their part be converted to other species, which can have deteriorated effects. Well, there is some knowledge on the internal of monopiles. Here I give an example from literature. Maybe the next slide can be shown. Yes, thank you. Here the right top shows some well, schematic profiles for a couple of important chemical and physical parameters, such as temperature, oxygen, conductivity. So something is known about these parameters. However, the obtaining of local measurement information can be quite a challenge in these environments. And of course, this is a very important thing to do. So obtaining more monitoring data is very important. And then, of course, oxygen was already mentioned a couple of times, which is a very important parameter. It was thought for some time that inside a closed monopile, oxygen would quickly go to zero. It was not as black as white as that. In many cases, there was some leakage or transport seen, and there's a lot of data which shows also that in many cases oxygen doesn't go to zero easily in closed systems. However, another important issue is also not only to look into the overall bulk of the internal monopile, but also look into certain niches. Such as near the seafloor or other anaerobic niches, where very specific locations can occur where oxygen can really be depleted to zero. And of course, here I show a picture already shown by Monica, which very nicely shows that if you have depletion of oxygen, replenishment holes can be an interesting option to counteract. Next slide, please. And I think this slide nicely relates to what Andrew Want showed very nicely on all kinds of biofouling. Well, I'm a microbiologist myself, and amongst other, I look into corrosion, also in monopiles. And there you see that inside the monopiles, and especially along the steel, you can have all kinds of micro niches where microorganisms like to colonize. And eventually it leads to the other biofouling processes that Andrew described very nicely. And what is very interesting, I think, is that you really also here you have to look at the different niches, aerobic, anaerobic, but also different environments, seawater, sediment, sand, and also the steel surface itself can be a very specific chemical environment, which leads to very specific growth. And if you look at the organisms that you find there, the bottom graphs show two analyses of findings in a laboratory setting, where we took reactors with seawater. And there you can see that you will find a variety of microorganisms there. And also, if you compare the left and the right graph, you see a difference when you go to the seawater or to a steel surface in that seawater. The specific niche will create a specific biofilm and a specific group of organisms colonizing. So with that, well, that's very briefly going into microbiology, which is eventually leading to other organisms as well, but just to touch upon it. With that, I want to pass the presentation back to Nick and go to the next slide, please.
Yeah, thanks, Stefan. As introduced by Stefan, there's a couple of well, downsides to adding cathodic protection to your monopile, besides protecting it against corrosion, of course. But especially with ICCPs, what we've seen is that the pH drops, and that this can and that dangerous gases can occur, and these need to be ventilated, or the water needs to be replenished. So what we've seen so far in the offshore wind industry is that in the design, water replenishment holes are added in the in the part of the monopile below the mean sea level, and that air replenishment holes are applied somewhere above the water level, but below the airtight platform. And these designs can, of course, be optimized because the unsteady marine environment, such as the waves, the tide, and the current, they drive basically together with the orientation of those holes and the size of those holes, how much water and air is flowing in and out of your monopile. What was touched upon by Andrew as well is that we have very limited information about marine growth, and then the DNV guideline that he showed was even only talking about marine growth on a vertical surface. If you can imagine that a steel monopile like this with maybe 8 meter diameters, the steel is about is almost 10 centimeters thick. So inside of your oval hole, which you make, there is basically also a horizontal surface of about 10 centimeters, which is also then exposed to quite significant flow velocities. About what type of species in such an environment will thrive, or and whether it will be a hard substrate or something soft, and how permeable it will be, there's quite limited actually known. And we do try to make an estimation on what it does eventually for your water replenishment, because we want to know how much new seawater flushes in with each waves. So as Stefan also said, a lot of new ideas for additional research or surveying offshore to get more insights into this. And then we can see whether or not we can optimize this replenishment and corrosion protection system, and maybe even add the nature inclusive design. So let's see if we can optimize this for a certain species of cod, for instance. Can we go to the next slide, please? So what we've done within the Altaris is done a couple of physical model tests. Here you can see where a blue dye was placed inside of a monopile, and that in this case there is only a tide going up and down, and there's a current. And because the internal free surface is allowed to, well, the holes are that big that internally the water is moving at the same pace at outward, that it's basically as sort of a pumping cylinder. It's pumping in and out the content of this cylinder in terms of volume. And what you would see if you add waves, that the amount of water is being replenished even a lot faster. What we've done is we've made a rather simple hydrodynamic model with which we can evaluate the amount of water that is replenished due to tide and waves, in which we take into account the vertical location of the holes and also the orientation with respect to the current and with respect to the waves. What we then can do with this information, that's on the next slide, I believe. Oh no, this was besides this simplistic hydrodynamic model, we can also do detailed CFD models, because what we see in some cases is that if you're in a certain storm condition, the waves get really high. If you then have quite significant water replenishment holes, like you sometimes see with the cable entry holes, which are up to a meter in diameter, that there's such a significant flow through these water replenishment holes that you get jet flows up to 10 meters per second. And I'm really wondering whether or not a cod sitting inside of your monopile will like it if there is a jet. But what you can also see from this detailed analysis is that actually outside of the area close to your hole, the flow is not that significant. So there is shelter inside of this large offshore structure. Then next slide. That's regarding the water quality model. We've seen from various people that some of the parameters of the seawater offshore are very important to promote certain habitats for instance, cod or lobster or some other organisms. What we can do with the water quality model is that by taking the water which is flushing in and out of our monopile, we feed this into the DELWAC, which is a Deltares built water quality model. And with that, we can model basically all of the chemical processes, including the ICCP, inside of your monopile, and then look at the effect on, for instance, pH, the dissolved oxygen, and all those other parameters, which are important for nature. What you see here on the lower left is first the HS signal, so that's the significant wave height over time for sea and as well, and that's for 4 months. And what you see in the top part, the more or less blue figure, you can see a couple of red lines, and red lines indicate the location of a ICCP anode, and then there is 2 white lines, and I hope those are visible. And at those 2 white lines, there is a replenishment hole. And we can see there's a bottom, that's the sea floor, and then there's mean sea level. And what we can see over time is the change in pH level in the bulk of the water over the vertical depth. So we can see, for instance, that after the 1st of May, there is a quiet period where there are hardly any waves. And we can see that especially near the bottom, below the lowest water replenishment hole, the pH drops quite significantly. And what we can combine this knowledge with is, for instance, what nature species like to settle at what period in time. And then we can see whether or not a certain water replenishment and cathodic protection system designed for offshore wind is then applicable for such a species. Then I have one final slide. Yeah, the next one, and then we can go over to discussions. So as said, yeah, this one indeed, regarding dissolved oxygen. But I think this was already mentioned by a couple of the colleagues, is that the oxygen over time will be variable, and it's affected by marine growth and the clogging up of those holes. So if the holes are clogged up significantly, then there's less new seawater coming in. And besides that, there's also a demand, of course, of oxygen. If you get more species and more biomass inside of your monopile, those will also have a larger uptake of oxygen, and there might be some kind of a balance. And I think that's it. I have a couple of things for the discussion on the next slide, but thank you for your attention.
Thank you very much, Nick. Thank you very much, Stefan. If we have one short question, we'll take it, but then otherwise we're going to turn it over to Jeff. So Jeff, I think that means what we'll do is Jeff will finish it off, etc. And then as part of that, we'll have a little bit of time, hopefully, for some broader discussion and for that questions to any of the people that presented either in part 1 or part 2. So over to you, Jeff.
Okay, thanks, Dan. And actually, first, thank you, Dan, for bringing us all together, because it's just been a fascinating hour and so many minutes. And I think the reassuring thing is all the joint knowledge from everyone who's presented really gives us an avenue to make better decisions as we move forward. So I'm Jeff Swain, Professor of Ocean Engineering at Florida Institute of Technology. Monica Meher, who you just recently heard from, and Kegler Erdogan, just very important in the research we've done and the knowledge we've gained. So our interest really is now, how do we manage the interactions between marine growth and internal water chemistry? And it's really following on from Nick's and Stefan's presentations, that how are we going to do this? And the way I look at it is to say, well, how do we perceive marine growths and the associated fauna? And typically as an engineer, you look upon it as biofouling. And it's something you want to control, it's something you want to maybe prevent. And the picture on the right is some blue mussel fouling of actually a seawater intake, taken in actually the late 70s of a seawater intake to one of the North Sea oil platforms. But I think nowadays we try and look upon it more as ecology. And really as engineers, how can we design to enhance and nurture nature? And again, the little picture on the right is of Lophelia pertusa, deep sea coral. And the irony is that again, in the 60s and 70s, trawlers basically decimated these deep sea coral reefs. And the arrival of the North Sea oil structures gave them a habitat. And I understand these corals are now flourishing on the oil and gas structures in the North Sea. And then finally, mariculture. Can we use these structures in any way to benefit sea creature production? The next slide. Well, I think we've heard so much about this, and the previous talkers have really given us a great insight into the factors that influence the biology of the internal space. So we look at it in terms of the structure, the monopile, the chemistry inside, and then if you have openings, what's the biology going to do? And then finally, how does this all interact with corrosion? And in the brief time I have available to me, if you look at the monopile, what I'm going to be focusing on is the dimensions. What is the influence of different diameters on the volume to surface area? When we look at chemistry, I'm just going to focus on oxygen. Oxygen is a prerequisite for life. And so if we want to look at it as a means to control biofouling, we reduce the oxygen. If we want to look at it in terms of ecological enhancement or mariculture, we obviously want to have oxygen concentrations that support life. The biology, well, we need to understand that, as Andrew so well taught us, in basically anticipating what will grow there. And the final diagram on the right is kind of interest to me. It actually comes from a researcher in the 70s, Kester, in 1974. And he basically defined the marine environment in terms of the redox potential, which you see on the y-axis in terms of potential, and pH. It was sort of a Poor-Bay diagram for the marine environment. And the little encircled area there is what we really like to work with. It's oceanic water. What we found in the enclosed monopiles, which have had cathodic protection, you're getting more into the lower pH, so it'd be more to the left, maybe acidic corrosion pits. And then if you get into the microbial-induced corrosion, then you get into the anoxic marine environments. So these sort of environments are fairly well defined and fairly well categorized. But as I said, for the short time I have, I'm just going to really focus on oxygen. So next slide. One of the things that fascinates me is if you look at the monopile internal space and you look at it with respect, again, the y-axis is volume in cubic meters, surface area in square meters, and you look at how these relate one to another with monopile diameter, you can see that the volume increases exponentially as you increase diameter, but the relationship to surface area is linear. Well, you might ask, well, why is this important? Well, when you think of it, the surface area determines that's where the reactions occur. It may be the reduction of oxygen with the corrosion reaction. It may be the reactions developing cathodic chalks, which occur when you apply cathodic protection. But now when we introduce biology, we're talking about metabolism and we're talking about respiration. And these reactants are supplied by the volume. So my sort of hypothesis is the larger diameter monopiles will have a larger volume to surface area ratio. And therefore, when we look at it in terms of oxygen depletion, it will be slower for the larger diameter piles. And I think the important thing to realize is we cannot treat, I believe, all monopiles the same. There's going to be a dynamics there that's going to be determined by the interactions of the volume and the surface area. Next slide. And so when we look at dissolved oxygen, there's been a lot of research in trying to understand, if you like, the anaerobic and depleted ocean space. And on your left, you have a figure that basically shows the interactions with oxygen saturation, say 7 to 8 milligrams per liter for normal and good biological activity, right down to 0 when we're getting into the anaerobic environment. And I should acknowledge the Virginia Institute of Marine Sciences for this figure. So basically, we now have a captured body of water. And what we want to do is to ensure that it is both a healthy environment if we're going to put in openings into the environment for the biology, and also that it doesn't go into the very low oxygen regime, say about 0.2 milligrams per liter, where you start to get hydrogen sulfide, anaerobic activity, sulfate reducing bacteria, etc. And one of the nice things about Monica's research, and you've already seen this figure a couple of times, is now we're looking at the dissolved oxygen in milligrams per liter on the y-axis and the duration of her experiment on the x-axis. And if you look at the perforated pipes, you'll see that as the biofouling started, or the biology started to develop on the inside of the pipe sections, we actually saw a depletion of the oxygen. And as Monica already said, we assume that was due to the sort of respiration activity of the organisms. And so when we design our perforations, we can either design them that maintain a dissolved oxygen level that is healthy for marine life, or actually we can design them to limit the ingress of oxygen, maybe to control biofouling. And that is, are you designing marine biology as biofouling, or are you designing these structures to enhance ecology? Next slide. Well, how does this relate to real life? And this is a bit of Don't take this graph too literally. But what I've said is, okay, Mytilus edulis, the blue mussel. What is the time to reduce oxygen to 2 milligrams per liter due to respiration? And on the x-axis, we have pile diameter. I've assumed an oxygen concentration in the ambient seawater is 7 milligrams per liter. I've assumed a muscle respiration of about 0.6 milligrams per hour and a muscle density of 400 individuals per square meter. I've assumed there's a linear relationship, which never happens in the real world with real biology. But the point I'm trying to make is that pile diameter does matter. And it does matter because of the volume to surface area ratio and how the reactants and the products of the reactions basically are buffered by the volume of seawater in which they are operating. Next slide. So where do we go? I mean, as I've already said, Dan, thank you so much. I mean, all these talks have been very enlightening. And I think it really gives us hope that our combined knowledge can really start to come up with some good models to manage the internal space. But to have models, you need numbers. And so ourselves, Dan, John, and Gudong from Tufts, and Colleen, Lena, and Loretta from the Woods Hole Institute, we're going to take Monica's initial experimental design. We're going to deploy some of these pipes up at the Woods Hole Institute. We're going to have another series down here with ourselves in Florida. And we're going to try and get more data, basically, that measures the impact of perforations on cathodic protection, corrosion and biofouling, impacts of coatings on cathodic protection, corrosion and biofouling, and then measure the impact of the biology on the conditions in the pipe and on the cathodic protection systems. So that is all I have. Try and merge the management with our knowledge and how we design these structures basically to perform well from a corrosion perspective, and also maybe to act as a means to enhance offshore ecology. So thank you, Dan, everyone.
Thank you, Jeff. And John, if you'll just go one more slide forward, that would be great. And so we do have a little bit of time, 12 minutes for a little bit of discussion. So I've put the agenda back up on here so that you can see the titles for the 4 presentations on part 1 and also what we discussed in part 2. What the research team is very keen is to sort of get your thoughts, get your ideas about what we should be doing next. Obviously, it's exciting to hear about what industry is doing, with Ørsted's example. That is tremendous, with Andrew, with the studies that he's engaged in, but obviously everybody who spoke today is their area of science or their area of leadership is critically important in order to ensure sort of responsible development and nature inclusive design. And I think there is a sense as described that certainly we can do this, but and be effective, but the science is complex. There's an incredible number of interactions, and we need to do additional work in order to understand it sufficiently so that we can do nature inclusive design with predictable results. And so right in the chat, what I'm going to do is I'm about to paste the survey that you would have seen before as distributed by email to get your thoughts on a few items. But we do have 10 or so minutes for some direct discussion now. And those can be questions to any of the people that spoke, or ideas you have, or thoughts that have been generated that you would like to share with those who are on the line together. So I'll stop talking there and we'll see how it goes. And John, my suggestion is maybe that we stop sharing, and so that those people who want to engage in this conversation and ask questions, we can see all the people in that way. So Peter, you have a question, go ahead.
I do have a very general one. And the question is, in what extent are these results site-specific? So do we have to carry out site-specific investigations in each situation? So I'm talking, of course, about Baltic Sea and North Sea, and others are talking about completely different areas of the world. This is my general question. I don't know who wants to answer this.
Dan, this is Jeff. I could give it a go because I think it's a very good question. And I think Andrew alluded to that when he showed the ecosystems of the world. And you're quite right, both in terms of seawater chemistry and in terms of biology. There are a great deal of differences. If you look at it just in terms of the DNV recommended practice for cathodic protection, for example, their practice will recommend different design for different sea areas just based on the oxygen concentration, seawater conductivity, etc. And I think when we get into the biology, we have an equal differential to make. So that would be my input. I think it's a very good question.
I can just add, I would say that, I mean, we have, there are a lot of knowledge gaps that do exist. In certain areas, we do obviously understand the biology and the chemistry better. Some areas are much better studied, other areas much less so. And I think another issue too, of course, is having databases which make it to facilitate this knowledge to be shared. This is something I think as generally as the industry can be improved.
And John, you had a comment or?
Yeah, I guess my apologies. Since I had the slides up, I haven't been able to monitor the chat. But one thing that I wanted to ask the group while we have a large group of people here is, I know I've been following for a while, and I know different countries in Europe have different requirements regards to like the corrosion protection system, particularly around anode selection, and like I believe it's partly tied to the environmental aspects of it. I'm wondering if, particularly for like internal water columns, if there's any potential concerns with like higher levels of zinc or higher levels of aluminum if you use some kind of galvanic system internally. And I know I've got one reference that talks about potentially having to investigate how it, interacts with the food web, but I'm wondering if anyone has any experience or knowledge in that space.
Stefan, Nick, you guys, I would look to you actually to say something about this.
Yeah, I was just pressing on unmute. But I know there have been some studies into this. A couple of papers have occurred. And I don't know them by heart, what the outcome was. For aluminum, the effect is not as critical as for zinc because a large part of it actually precipitates and becomes non-bioavailable. However, I would recommend to make an overview of these papers that occurred. And I also know of a project that Deltares was involved in, where in general environmental emissions from offshore wind activities were explored. And well, what I heard from colleagues was that the impacts were relatively low still. So that's optimistic at least. But of course, we discussed this with colleagues also last week. And what is very important also in public acceptance is that that clear data is shown on the effects, so that when with regards to metals, of course, the idea is, well, it's toxic and effects, and it's very important then to come up with detailed knowledge about this. And one other thing is because I saw in the Menti questionnaire, one of the questions raised was already if there are negative effects, should offshore wind be limited or well? And I think an important thing is that there's a lot of things that can be done with mitigation, and also the choice for different. If you, for instance, look for corrosion protection options that you have different choices, and so even if you come to the conclusion that certain options have bad consequences for the environment, in many cases there are also options to choose for different types of protection systems, or to choose a way to mitigate effects. And I think that that's very important. Sorry about the long answer, but it's a lot interesting things to.
Thank you.
Jeff, we'll give you a sort of maybe a last word there, and then I'll just make a closing comment and we'll complete the workshop.
Yeah, I was curious, how widely have the water replenishment holes been embraced in Europe? And have people gone back and retrofitted, if you like, holes into existing structures? So I don't know if this is a question for Nick and Stefan or anyone else out there. Thank you.
I think I can take that one. I think in general, the water replenishment holes have been quite widely accepted. What we see in current offshore wind monopiles, retrofitting of holes in monopiles I've not seen, because I can imagine that it's quite an impossible task, I would say. What we do have heard of in some cases is that by using both the water replenishment holes and the really new and innovative coatings, is that people wait with applying ICCP. So they make a design for a certain monopile with replenishment holes, and that the ICCP system is actually only later deployed. In some cases, you might have a combination of cathodic protection with sacrificial anodes, which are there first, and then later applying ICCP, because you can imagine the ICCP only works by the time you have power, and the foundation goes in at the start of your project. So you have to bridge a gap, either by applying a really good coating or having sacrificial anodes in place. That's at least my current state of what the design looks like.
Nick, thank you very much. And since we're 1 minute away, what I'll do is I'll have a little bit of closure. First of all, thank you to the speakers. That was really, in my opinion, really amazing and inspiring. So much promise for the future. And so, obviously this workshop was not about getting to all the technical details. When Jeff and I were talking about this a day or so ago, we were saying, looking at everybody presented, what we need is a 2-day workshop. So we do look forward to your ideas of what would make sense for the next steps in this. And we'll be working on ideas and trying to get proposals out there to get the community together on a number of these items. So there is a survey, please complete it if you can. There will be another workshop in about a month. That's going to be looking at structural aspects associated with the use of perforations and what might be an optimal level. As some of you may know, there's investigations if you look at large diameter monopiles in deep water, their design is controlled by wave loading. And so people are looking at the impact of perforations on reducing the peaks of the wave loads by distributing it out over a course of time. As Dotaris mentioned, You know, if you have small holes, you can get water jets at 10 meters per second. If you completely open it up a large amount, the wave just goes through. And so we've been in conversation with some fabricators about what might be an optimal level. So we'll be getting into some of the structural design issues, stress concentrations, buckling, when you have perforations, et cetera, in the next workshop. We'll probably have a one after that, which is starting to look at what types of field and laboratory studies are needed to further advance the science. So my sincere gratitude to everybody who put in so much time today, and for everybody else who came and participated in the workshop. We'll do our best to answer all your questions. I'm going to leave the Zoom open for a couple of minutes so that people have the opportunity to share some thoughts that may have come to mind, some questions that they didn't get a chance to ask, etc. But otherwise, I know people are going to be disappearing. So thank you again to everyone.
Thank you so much. Bye-bye.
Thanks, Dan.
Thank you, Dan.
Thanks for organizing.
Bye-bye.
Thank you.
Thank you.
Thank you. Nice day.
Great job, Dan.
Thanks a lot. See you all.
Yeah, Dan, it's going to take a bit longer for this since there's actually files in the chat window.